Okay, so welcome back, everybody. Today I am going to continue the slides on Chapter 3, Computer Arithmetic. If you looked at my little show for last week on Thursday, which very few of you went to look at, I'm afraid, you should go and take a look. I talked about significant digits and precision of computers. Today I'm going to recall or define exponential form, which is used in the computer to store real numbers. And we're going to start looking at how internal storage works for numbers. So let's see. So exponential form, if you are familiar with scientific notation, exponential form, the normalized version that we're going to look at is the same. So let's just review a few basic things in decimal. The basic principles in binary will be the same, okay? So if you have a number written in decimal and you multiply it by 10 to the power n, right? So that means that you're going to shift the decimal point, right? And if it's a positive number, then you're going to shift the decimal point to the right by that many places. And if it's negative, then you're going to shift the point to the left by that many places, right? So I have a few examples here, which are 5.67 times 10 power 2. So we have a positive, I don't know why I'm speaking like that, positive exponent 2. So that means you shift the point to the right by 2 spots. So that's 567. 5.19 times 10 to the power negative 3. Exponent is negative. So that means that you're shifting the point left by 3 spaces. So that's 0.00519. And so on, right? So I assume all you guys are familiar with this. And so let's see now the exponential form theorem. That looks really nasty and fancy and complicated, but it's not, okay? Sorry, I'm still admitting people in here. Okay, here we go. All right, so here's the result that we're invoking. So if you take a real number, a, any real number, a, which is non-zero, then you can write this number in a unique way, which is called normalized exponential form, or also scientific notation, which you have probably seen. If you write your number as follows, so it is of the form m times 10 to the power n, okay? Where in m, the decimal point appears directly after the first non-zero digit. So your number a is non-zero, so certainly when you write it down, there's a non-zero digit, okay? So you move your point to right after the first non-zero digit, and then you'll adjust the exponent, right? So here is a very important remark. Your textbook uses something called normalized exponential form, okay, which is different. The decimal point in the book, the decimal point appears right in front of the first non-zero digit. That's an old standard that was used many years ago in computers. It is not what is used now. So what I'm going to show you is the IEEE 754 standard, which is the one used in all computers today. And it uses the normalized exponential form that I've just mentioned right here, okay? So this is the correct one. So if you look at the list of exercises, I've included corrected versions of the solutions in there, okay? Okay, so let's define a few terms here. So the number m, so if you wrote your number a in exponential form, then in normalized exponential form, I should say, then the number m there is called the mantissa, and the little n there is called the exponent. Of course, it's an integer, all right? The mantissa will always be, so suppose your number is positive, then your number will be something point something, so it's at least 1, right? So it's 1 point something, can't start with a 0. And it'll be less than 10 because we have only 1 digit before the point, right? And if negative, then it's the other way around, okay? So here are some examples of this. So suppose I take the number 222.2 and I want to write it in normalized exponential form. So what I need to do is move that decimal point to the right of the first non-zero digit, right? And of course, adjust the exponent accordingly. So this is 2.222 times 10 power 2, right? It's the same number. So that's its normalized exponential form, okay? So I bet you've done this before, okay? 0.0033, right? If I want to write it in normalized form, then I need to move that point 3 steps to the right, and I have to adjust the exponent of 10 accordingly. So since I'm making the number bigger by moving this point, I need to reduce, or in other words, put a negative exponent. So that's 3.3 times 10 to the negative 3. Okay, so that's how I see it. So if I'm modifying the position of the point, if I'm making things bigger, but I want to keep everything the same, then I need to decrease in the exponent, so it's negative, okay? Minus 44.44. So I need to move that point 1 step to the left, making that number smaller if I do that. So I need to compensate by pushing up the exponent by 1. So that's minus 4.444 times 10 power 1, right? So these numbers are the same, okay? 5.5, is the point in the right place? Yes. So what's the exponent of what's the power of 10 we're using?
10 to the power of 0.
Correct, power 0, right? So nothing happens, we're not changing anything. So this is 5.5 times 10 power 0, okay? And finally, one last example, minus 0.00006. I need to move that point 5 steps to the right, which is making the number, if I were just to move that point, I would make the whole thing bigger. So I need to compensate in the exponent. So that's minus 6.0 times 10 power minus 5. Okay, so I've written all these numbers in standard exponential form. Okay. Now, just one little comment. You will see this notation often, this E notation, and that stands for this notation here, right? So if you see 11.23 E3 on a calculator, not all calculators use that, but some do. That means 11.23 times 10 power 3. By the way, the example there, 11.23 times 10 power 3 is not in the exponential form we want, right? We'd have to modify that slightly. We'll get back to that. Okay, so arithmetic in exponential form, how does it work? So we're going to look at multiplication, division, subtraction, addition, right? But this is something else that you've probably done also, but it's pretty straightforward, right? So let's start with the simplest of all the operations in this form. It's multiplication. So how do you multiply two numbers written in this form? Then you multiply the mantissas and you add the exponents, right? When you're multiplying 10 to the power n times 10 to the power m, it is 10 to the power n plus m, right? So here is an example. Here we go. So 7.34 times 10 power 6 multiplied by 2.1 times 10 to the power negative 4. So what do? I can just reorder. So I don't like this slide, but I'll leave it like that. But as written now, if you take a snapshot of the slide right now, it's false, right? What's written is not true. So I'm just going to multiply the two mantisses first. 7.34 times 2.1, which is 15.414. Okay. What's missing are the exponents. Now this is a little better. So 10 power 6 times 10 to the power negative 4. When I'm multiplying these, what do? I add these powers. And here it's 6 minus 4, which is 10 power 2. Okay. So very, very straightforward. Okay. And you can always think, so how would the machine do this? Well, if it has the numbers, if it has the mantisses and exponents, then I can just multiply the mantisses and add the exponents. It's easy, right? The last step, if we want to rewrite this in normalized exponential form, we have to rewrite this last number. There are too many decimal places to the left of the point. I need to compensate, right? So I need to move that point to the left by 1. And so I would be making that number smaller. So I have to push up the exponent by 1, right? So that's 1.5414 times 10 power 3, okay? Now, notice that the number of digits, just a little remark here, we'll see a little later that the number of bits, if you want, the number of digits that we can keep for the mantisses is fixed, right, in the machine. So when you're multiplying, you're going to get very probably way more digits than you can actually keep. So this is where what I talked about in the last lecture, if you looked at it, where you need to truncate or round, okay? So, okay, so that's multiplication. That's pretty straightforward. For division, it's the same thing, right? You divide the mantisses and you subtract the exponents. So that's basically the same principle, okay? I don't think you'll have to do that by hand at any point, okay? So not division, that's for sure. Okay, addition and subtraction, different? So the only way you can do this is if you have the same exponents. That power of 10 has to be the same for you to do anything with this. So what do you need to do is if you have two numbers, you have to rewrite one of them so that the exponents will match, and then you add and subtract the mantisses, okay? So usually the exponent which is changed is the smaller one. So let me show you an example. So let's say you have to add 3.14 times 10 power 3. This is in normalized exponential form, and you want to add 7.4 times 10 power 5. So the exponents are different, so you can't do anything until you make those exponents the same, right? So you compare the exponents and modify then the one which is the smaller one. So what you do is this. So you rewrite that number, 3.14 times 10 power 3. You want to rewrite it so that you have 10 power 5. Now, if you're making the exponent bigger, you have to compensate by making the mantissa smaller. So you're going to move that point to the left, right, by 2, okay? So 3.14 times 10 power 3 is the same as 0.0314 times 10 power 5. You can always, you know, if you're not sure, just look at the two numbers and say, okay, can I go from one to the other easily? And if yes, then you know you got it, okay? So now you have the same exponent, so all you have to do is add the mantisses, you add them up, and of course it's times 10 to that same power you have, 10 power 5 here. So you get, in this case, 7.4314 times 10 power 5. Notice again that we started off with two numbers. These are very small examples, but the two numbers we had, one of them had three digits, and the other 2 in the mantisses, and we end up with an answer with 5 digits, right? So if you think of a fixed amount of space for your mantisses, which is what we will have, then you'll have to do something. The machine has to drop some digits in some way, either truncate or round, like we saw. Okay. All right. So I'm going to redo exactly what I did now, but in binary, but it's exactly the same thing. Okay, it's the same principle, but rather than working with powers of 10, right, binary works with powers of 2. Okay, so shifting yes. Can you mute your phone, please? Thank you. So if you look at the slides, you'll see that I basically just cut and pasted. It's the same thing, right? You just switch 10 for 2, 2 for 10, I should say. Okay, so so again, if you multiply a binary number written in binary, if you multiply it by 2 to the power n, that means that you're going to shift the point by that number of places. If it's positive, you're shifting to the right, and if your exponent is negative, you're shifting to the left. Okay, so I have some examples here. So 1.01 times 2 power 2. So the exponent is positive, so I shift the point to the right by 2, right? 1.11 times 2 power negative 3. Exponent is negative, so I'm shifting left by 3, so I get 0.00111. Everything here is in binary, okay? Well, except when I'm writing times 2 to the power, that part is written in decimal, but the mantissa is written in binary. So hopefully this is not confusing. I don't think it should. I don't think it is, but 0.0011 times 2 power 5, then the exponent is positive, so you're shifting the point by 5 steps to the right, so you get 110, okay, and so on. So it's the same thing, except shifting means powers of 2, okay? So now here's the exponential form theorem. So why are we doing it in binary? Because, well, the machine, the numbers are in binary in the machine, right? So when we're talking about exponential form in the IEEE standard, it's this one, okay? So I talked about the decimal one because we're used to that, right? So it makes more sense to us because we're very much used to base 10, but this is this is the result which is used for the internal representation of numbers, okay? So here's the theorem, it's the same. If you take a number a, any real number a, which is not 0, okay, you can write it in a unique way in what's called normalized exponential. Mute.
Why don't you mute?
No, the dog wasn't here. No, somewhere. So one of my students just got eaten by a dog. Okay, all right. So yes, what was I saying? Normalized exponential form binary. So you can write any, your real number a, which is non-zero, you can write it as m times 2 power n, okay? And in m, the binary point appears directly after the first non-zero bit, okay? So it's the same principle as in decimal. Notice the advantage here, which is very nice, is that there's only one non-zero possibility, right? It's 1, right? In decimal, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9. But in binary, it's just 1. So you know your number will be 1 point something. Okay, so that's for sure. Okay, so again, m here is called the mantissa and n is called the exponent in this form. And here are some examples. Okay, so 111.1, this is in binary, right? How do you rewrite that? Well, I want to rewrite with the binary point right after the first one. So I need to shift it left by 2, but I need to keep everything equal, right? So if I'm shifting left, I'm making the number smaller. So I need to pump up the exponent to keep everything correct. So this is 1.111 times 2 power 2. Again, I repeat, this is like a mixed weird notation where the mantissa is written in binary and 2 power 2 is obviously in decimal, right? But it should be clear what's going on here. Okay. 0.0011. If I want that in exponential form, in normalized exponential form, I need that point to be, just a sec. Oh, I got a chat here. Oh, okay. Yes, that happens. What, was that your dog? Went nuts? Okay. I'll close. Sorry, because I have these slides, I'm hiding my little panel, so I don't see if chats are coming in, I'm afraid. So if you just try to alert me verbally, because the panel gets in the way of my slides. Really annoying. Okay. All right, so 0.0011, I need to shift that binary point 3 steps to the right. That would make the number bigger if I didn't compensate in the exponent, so the exponent will be negative. So this is the same as 1.1 times 2 negative 3. Minus 1, notice I don't say 11, it's not 11, it's 1, 1, right? It's in binary. So minus 1, 1.101. I'm going to shift that point once to the left. I compensate by a 1 in the exponent. 1.001. And you can see basically what I did is I just cut pasted the decimal examples and I replaced all the non-zero digits by 1. That's exactly what I did. Okay. 1.001 will be 1.001 times 2 power 0, right? So there's nothing to change in the exponent. And finally, minus 0.00001. I need to shift that point 5 spaces, 1, 2, 3, 4, 5 spaces to the right. So this is minus 1.0 times 2 power negative 5. Okay, so it's exactly the same thing as decimal, except it's powers of 2. Okay, all right. Internal representation. Let me just check the time here. Okay. Okay, so what I'm going to show you now is the current version of the IEEE 754 standard. So this is what is used in machines today. The number of bits used might vary from machine to machine. I'm going to show you on 32 bits. Okay, we could do it in more general. If you look at the Wikipedia page for the IEEE 754 standard, not a bad idea to go take a look. It looks way more complicated because they are doing it independently of the number of bits. So they're trying to do it in general for whatever number of bits the machine uses, but it gets a little heavy. So we're going to do it on 32 bits. So the numbers are fixed. It's easier. You can, if you understand how it works for 32 bits, you can figure out how it works for 64 bits. No problem. Okay. The way numbers are kept in memory is normal straight binary. It's not BCD here. Okay, there is no BCD for arithmetic operations. However, the way that numbers are stored is very different if you're thinking of integers or real numbers. Okay, the way that the numbers are encoded in the machine is completely different. Okay, and once I've shown you, I will explain the difference between the two in how they compare. Okay. All right, so let's start with the easier one of the two, which is integers. Okay, so whole numbers, right? Positive, negative, or 0. Okay, so no fractions, no decimals if you want. Okay, the basic thing is if you have a positive integer, you just write it down in binary on 32 bits. If it's negative, what do? You use the 2's complement, right? So that's it. That's the standard. That's very, very simple. Okay. So for example, if you have 423, how is it stored as an integer in the machine on 32 bits? Well, you convert 423 to binary, which will be 1101001111. If you look at that last part there, and you write down on 32 bits. So of course you're padding on the left. The zeros at the beginning, of course, don't contribute anything, right? How do you store minus 423? And you take the 2's complement of, on 32 bits of 423. So you look at those 32 bits that we wrote, that whole bunch of zeros and 1101, 00111. What's the 2's complement? Again, you flip all the bits and you add 1. And that's how you write minus 423 in the computer. That's how it's memorized, if you wish. Okay. So now notice here are some here are some remarks and advantages, disadvantages, or whatever, some comments on this way of representing integers in the machine. Okay, so at the top I put the previous example. So first of all, the machine can tell if a number is negative or positive very quickly. All it has to do is look at the first bit. Okay, so the first bit is 1, means the number is negative. So we put a bound on the largest positive number that we represent on 32 bits, which is 0 and all ones after. Okay, so if it's 32 bits, this number is quite large. It's 2 power 31 minus 1. So it's 1 less than 2 to the power 31. It's a very, very big number. Okay, so this is the biggest positive number that you can write on 32 bits. Okay, if you take the 2's complement of this number, right, so flip all the bits, you're going to get 1 with all zeros. Then add 1 to that, and it's the number which you see right over here. Okay, so 1, all zeros, and ends with 1. So this is the internal representation of negative 2 to the power 31 minus 1. You see it starts with a 1. Okay, so your positive numbers start with 0, as all zeros also. Okay, and if you take the complement, you start with a 1 immediately, and then you get a negative. Okay, now notice, so if you want to see how this goes with small, just try on 3 bits or 4 bits, and you can play with this. It's easier than with 32 bits, right? And you'll see that all the sequences of zeros and ones are used except one. There is one sequence which is not used, like this, which is 1 followed by all zeros, okay? Which is used for something else if you want to. I mean, we won't talk about it here, but go look up the IEEE article sorry, the Wikipedia article on the IEEE standard. This is used so-called negative 0, but I'm not going to talk about that. Okay. So all sequences are used on 32 bits except that one. Okay, and you can see that you can't obtain this as the 2's complement of any number. Okay, it's not possible. Okay, so that's integers. That's really straightforward. So what's the nice thing about writing negative numbers in 2's complement is that the basic operations will just work out immediately, right? So if you have, let's say you have 2 numbers to add, one of them happens to be negative, right? So it'll be written in 2's complement. So you'll just add them together, and that's exactly how we subtract, right? So that it works out very nicely. Okay. Floating point. So we looked at integers, whole numbers, if you wish, and now we're going to look at real numbers, right? So this is what we call floating point. Okay, so what we're going to try to do is write down in the machine that normalized exponential form that we had. Okay, and what I'm going to do is I'm going to define exactly everything how it works, and then I'm going to work through an example from start to finish. Okay, so I'm going to take a real number in decimal, and I'm going to show you the 32 bits of how it's handled in the computer at the very end. Okay, so we have 32 bits, which are separated in 3 different fields. The first field is the sign bit, super easy, right? So it's 1 if you have a negative number, and it's 0 otherwise, okay? So this is the sign bit, it's the leftmost bit of your 32 bits. The next 8 bits, second field, is for the exponent, or not quite. Actually, it's for the characteristic. I'm going to talk about that in just a sec, okay? So it's not quite the exponent, it's a tweak of the exponent. And finally, the 23 bits that remain, this will be the mantissa, okay? Now, here's a remark. I talked about significant digits in that lecture that very few of you have looked at. Go look at it. So the precision of a computer, if you're working with 32 bits, then you have a 23-bit mantissa, then the precision of your computer is 7 significant digits. What does that mean? Okay, so the mantissa contains the significant part of the number. The exponent is not part of that. If you think about what significant digits mean, it's really the mantissa that contains that. Now, we compute significant digits in decimal. So what's the biggest number that you can write on the mantissa, right? Or it's 2 to the 23, which is 8388608 in decimal, and that's 7 decimal digits, okay? So that's the precision of the computer if you're working with a floating point on 32 bits. Okay, all right. So now, exponent biasing. So this is the last little thing before I work out the example. So we've got the sign bit, that's easy. We've got the mantissa, all right. Now the exponent, the machines. So if you remember, I said this first line in the slide says see later, but it's see before actually. When you are adding 2 numbers in exponential form, you have to look at the exponents and compare them, okay? If you're using 2's complements for negatives, it makes it more complicated for the machine to compare quickly. So what the engineers came up with is they're biasing the exponent to make it easier to compare. So what's the bias? You just add a number, you shift all these numbers by a certain amount to make it easier to compare. So how does this work? Okay, so we have 8 bits for the exponent field, okay? So this, so if you, if you, I wish I could figure out a way of sharing 2 screens at the same time, which is possible, but, so the biggest exponent that you can write on 8 bits, think of when we did it on 32 bits, it was 2 to the 31 minus 1. For 8 bits, it'll be 127, which is 128 minus 1, okay? Now, you say there's minus 126 here. This is the IEEE standard. Minus 127 is not used, okay? So at the very bottom of the slide, you see that there are 2 sequences of 8 bits that are not used or used for something else. We won't deal with that, okay? So the exponent can be any value between minus 126 and plus 127, okay? By using that 2's complement trick again. But how do you store the exponent? You add 127. And the result is called the characteristic. It's just a name, okay? It's just the name which is given to this. So in the table, you see that the exponent can be anything from minus 126 to 127. You add 127 to this. So you're going to get numbers from 1 to 254. And there, I've written them on 8 bits there in binary, okay? So these are all the possibilities. So this is what is stored. It is the real exponent plus 127. That's how this is stored. Why? Because then it makes it much easier to compare the exponents because it gets rid, in a sense, of the 2's complement. Okay. When the machine starts doing arithmetic, then it knows that it has to remove this bias, this plus 127. It knows it's all built in the hardware, actually, software/hardware, that it needs to remove this before it starts playing with the numbers. Okay. All right. So to illustrate this whole thing, I'm going to do an example. You'll see it's not super, this is not hard. Okay, there's just lots of little itty bitty things all over the place. Okay, so the number A that I have is minus 419.8125. And I want to know exactly what the contents of the 32-bit register in the computer will be for that number. That's what I want to know. Okay, so this is written in decimal, so obviously I need to write that in binary. Okay, so in theory, you guys know how to do this. Just paper, pencil, you can do it. Okay, so this is minus 1101000011.1101. This is that number in binary. Okay, next step, I need to write it in normalized exponential form. That's not hard, right? All I have to do is shift that point so that it is to the right of the first non-zero bit. I do that, okay? So in normalized exponential form, the number that I'm looking at is minus 1.101000011111101 times 2 power 8, okay? So now I have my mantissa, I have my exponent, and I have my sign. I have all I need to get those 32 bits, okay? So this is the mantissa, minus 1 point blah, blah, blah. The exponent is 8, and the sign is negative, right? Okay, so what's the characteristic? I shift by 127. So my exponent here is 8, the real exponent is 8, but I shift that by 127 to store it in the machine. Okay, so now the resulting sequence of 8 bits is 100000111. Okay, and so, okay, so this is my number A, mantissa, characteristic. I'm just repeating what I just put on the previous slide. So here is now the contents of the 32 bits. There's one last thing that there are a couple of things that you need to be careful with. Okay, I've seen a lot of mistakes on tests in the previous years with this, and I really don't want to see this mistake. Okay, so the mantissa is a fraction, right? So you don't pad it to the left with zeros. This is going to mess it up completely. You want to pad it to the right. If you have, right, think in decimal. If you get 0.25, 0.25000000, it doesn't change anything to the value, but 0.00000025, that's bad, as you're making this much smaller, right? So it's important that when you write down your mantissa on those 23 bits, you pad with zeros to the right, okay? The second thing, and this is important, that first one, right? That's the advantage of binary on decimal. One advantage of binary over decimal here is that you know that first non-zero digit is a 1, right? So the computer doesn't need to memorize that 1. It knows it's there, right? So you just don't memorize it. You just put only the fraction part, okay? So what is kept in memory on the 23 bits is that part to the right of the binary point. That's all, okay? The number is negative, so that first bit is 1, and the exponent plus 127, that's a characteristic we computed earlier, is 10000111. So the register, the 32-bit register, is exactly what you see at the bottom of the slide here. I put the sign bit in blue, the characteristic in red, and the mantissa is in black. It's, again, it's not quite the mantissa, right? There's the 1 point, etc. So that's the fractional part. That's the fractional part of the mantissa, I should say. Okay, So these are the bits for that number. Or, yep, there's a question. No, just okay. Now, last slide. Comparison between the integer version and the floating point version. If I give you an integer like 405, then it's also a real number, right? It doesn't have a fractional part, but you could write it in floating point in the machine, right? So here I computed both ways of writing. You see it's completely different, right? So 405 as an integer is just straightforward binary. There it is, okay? So there's a whole bunch of zeros at the beginning, obviously, because it's a small number. Now, if you write it in floating point, then you have to write in binary, you have to write in normalized exponential form, what's the exponent, what's the mantissa, blah, blah, blah. This is what you're going to get. Now, what's the difference? Well, the thing is the choice is always, it's always better to work with integers if what you have are integers. The machine is way more efficient with integers than it is with floating point, okay? You see that the computations for floating point have to take longer because you have the exponent, the mantissa, the sign. It's going to take longer. And when you're working with floating point, you're going to get truncations, right? You have less information in a sense on those 32 bits. So you're going to chop off some values when you're doing a lot of number crunching. So obviously, if you're working only with integers, it's better to store them as integers. Okay, so that's the difference between the two. That's basically it for that. Okay. So that's the end of those slides, end of the lecture, and that's the end of the material for the first test, which is in 2 weeks. Okay. Tonight there's a WebWorks that's closing. Some of you should get to it. I'll give you some time right now to go and work on that. And I'm going to open up a new WebWorks on BCD codes and ASCII in a few minutes for this week. Okay. Are there any questions, comments?
For what you had said about integers earlier, does that have anything to do with the overflow glitches that sometimes occur on older computers and games? The sort where if a number is represented in 8 bits, adding 1 to 255 gets you 0 because it overflows. Does that have anything to do with that?
Sorry, you'll have to just give me one little sec. No, this is okay. Sorry.